Hello everyone, welcome back to the course on machine learning using Python programming. In this lecture, we will see ensemble learning, and that is very popular. Its performance is very high, and when we have seen Occam's razor principle, in that we have seen generally we have better performance when we use ensemble learning techniques. The content are taken from these websites. So, we will see first of all what is ensemble. Ensemble is a group of predictors or group of machine learning models. So, here what happens, we train all these models or all these predictors. In case of other machine learning techniques, what we have seen, we create a single model and that model is trained, and then on the same model we predict for the new instance. While in case of ensemble learning, we have more than one models, and then we train all these models, and then prediction is also done in models, and then for the final output we take aggregation of all these outputs of all these prediction models, and that aggregated output is the final output in case of ensemble learning. So, we can say that this aggregation function can be statistical mode, that is also called as hard voting in case of classification, and average in case of regression. So, if it is the regression problem, in that case if we are using ensemble learning technique, then we will take average of the output of all the predictors, while in case of classification we take the statistical mode of the output of all the predictors. So, this is called as a hard voting classifier, means the class that is getting more weights from predictors, that class we will give as an output. So, here we can say that if we use individual machine learning model for training and then testing, when we will compare it with ensemble learning, and in ensemble learning you have all different predictors or machine learning models that are suppose not that much strong, these are weak machine learning models. Even then when we will combine them, and we will get results by aggregating output of these predictors, then the performance gets better. So, this ensemble learning is one of the most popular technique. So, we can say that if each predictor is a weak learner, we are assuming that in the ensemble we are using weak predictors. It means the models that we are taking are not very strong models, very complex models. Even then when this ensemble can be strong learner, but these two conditions must be satisfied, then only we can say that your ensemble machine learning technique output will be better than a single machine learning model. So, these are the two conditions, that number of weak learners are sufficient. So, means we may need to take many machine learning models and then combine them to form ensemble learning technique, and the second condition is they are sufficiently diverse. So, definitely the idea is that if one machine learning model is suppose giving you wrong result for one particular instance, then rest of the models should give correct result, and then when we will take aggregation we may get correct one. If all the models are working in the same way, so it means results of all the models will be same. In that case, when we will aggregate, there will be no improvement, and that is why this is the second condition, that all these models must be sufficiently diverse. So, now there are two cases for producing the output. In case of classification, this is hard voting classifier or it can be soft voting classifier. So, in case of hard voting classifier, what we are doing? We are aggregating the predictions of each classifier and we are predicting the class of the new instance that is getting most votes. So, it means most of the classifiers are giving the same class for the new instance and that class we will give as an output. So, this is called as hard voting classifier, and we can say that this voting classifier often achieves a high accuracy than best classifier in the ensemble. So, in the ensemble we will have many base classifiers and your final voting classifier output will be better than the best classifier that you have as one of the base classifier in your ensemble. So, now we will see what is soft voting classifier. In case of soft voting classifier, if all the classifiers are able to estimate class probabilities. So, here we are not assuming that the output of the each base classifier is exactly the class name. Means if we talk about binary classification, so your predictor output is not 0 or 1, it is the probability of belonging to class 0 or class 1. Then we can predict the class of this using this ensemble method, we can predict the class with the highest class probability averaged over all the individual classifiers. So, we will find the average probability and the class for which this probability is highest, that class we will provide as an output, and this is called as soft voting classifier. So, here let us see one I want to see why soft voting classifier can be better than hard voting classifier, because suppose in case of hard voting classifier we are taking in ensemble, we are suppose taking 3 base classifiers, 3 predictors and one predictor is giving you class as an output class 1 for a new instance, another predictor is giving you class 0 and the third predictor is also giving class 1. So, here hard voting classifier will give you the final class as 1 for the new instance, because there are 2 votes for class 1 and 1 vote for class 0. While if we talk about soft voting classifier and again we are taking 3 predictors in the ensemble, then your first classifier is suggesting that there is suppose there is a 20% chance that the class is 1. The second predictor is saying there is 90% chance the class is 0, and this is saying there is 60% chance that the class is 1. So, here for predictor 1, 20% chances it is saying that the class is 1 and 80% chances are class is 0. For predictor 2, 90% chances are that the class is 0 and 10% chance is the class is 1, and for third predictor 60% chances are that the class is 1 and remaining 40% chances are for class 0. So, we will take the average of all class probabilities for class 0 as well as class probabilities for class 1 for all the 3 predictors, and whichever will be more we will assign that class in soft voting classifier. So, now we will see another concept of ensemble learning, that is bagging and pasting. So, what is difference between bagging and pasting we will see, but we know that in ensemble learning techniques what we want, all the classifiers or all the predictors in general, because it can be used for regression problem also. So, what we want, all these predictors must be diverse, and how we can do this? We can achieve this diversity in different predictors. This can be done using different training algorithms, means we can have different predictors, like one predictor as a base predictor we can use, suppose decision tree, and second one we are using naive Bayes suppose classifier, another one we are using suppose SVM. So, we can use different predictors, and the second possibility is that we will use the same training algorithm, means all the predictors are decision tree, but we are training them on different random subsets of the training set. So, training set is divided in different sets, and your predictors are being trained on different part of training sets. So, when we are creating random subsets of training set, if we are using we are performing this sampling with replacement, then this is called as bagging, or in this is basically bootstrap aggregating. So, in short we say it is a bagging. If this sampling we are doing as without a replacement, then it is called as pasting. So, here we are saying that your models may be same or different, but basically the training the set on which we are training those different predictors are different, and the set that we are creating for different predictors, if we are creating it with replacement, it is called as bagging, otherwise it is called as pasting, means if it is without replacement, it is called as pasting. So, generally we can say that in case of bagging and pasting, definitely your each predictor has high bias. Why high bias? Because now the training set is reduced, the whole original training set was large, but we are giving some samples of that to different predictors, and that is why each predictor has now higher bias, but when we are aggregating output of these and getting the final output, so we can say that variance is less. So, bias error is increased, but variance error is now reduced. So, generally in ensemble learning we will see that bias is not that much increased, it is generally similar bias, but variance error becomes less, and that is why this ensemble learning technique is we use it because we get lower variance error. And these ensemble learning techniques are scalable also, because these here we are using many predictors, many Bayes machine learning models. So, these predictors or machine learning models can be trained in parallel. So, if we have different cores, on different cores CPU cores, we can train parallelly all these models, and then during prediction also, when we are predicting for a new instance, prediction on all these different models can be done parallelly, and that is why we can say that it is scalable also. Now, we will see the concept of out of bag evaluation. So, generally when we are doing sampling and we are giving some part of the training data to each and every predictor. So, what happens, there are some instances that are not given to that predictor, and those remaining training instances that are not given or not sampled are called as out of box instances. So, these out of box instances definitely will be different for different predictors. For for one predictor this set will be different, for another predictor this out of bag set will be different, but we can use this set as a validation set. So, you do not need much data, we are creating validator, we can create validation set out of this training set itself if we are using bagging or pasting. So, now we can evaluate the whole ensemble model also by taking the average out of this out of box evaluation of each predictor. So, in this way, this is the concept of out of bag evaluation, means we do not need to create validation set initially. The remaining instances that were not sampled for the predictors, those can be used as a validation purpose. Now there is a concept of random patches and random subspaces also. So to make these base machine learning models more diverse, what we can do, we can sample features also. Means one model we will train on, suppose starting 100 features, and the second model we can train on remaining features. So we can say that, and definitely we can do it if your data set is high dimensional data set, means number of features are very large, otherwise it will not be possible. So when we say it is a random patch method, when sampling is done for training instances as well as for features, means each and every base machine learning model is getting only few training instances and only few features, while random subspaces is called when we are giving all the training instances to all the models, but features are different, means we are sampling only features, then it is called as random sample space. So now we will see the first and that is most common ensemble learning technique, that is random forest. So what is this random forest? In general, ensemble learning technique has so many base machine learning models. So in case of random forest, all the base models are decision tree models. So it is an ensemble of decision trees, and generally in case of random forest, we say that it will be trained via the bagging method. So here bagging method we use for the training, and then predictions, how we will do the prediction, it is same as we have seen in case of general ensemble method. So we will obtain predictions of all individual trees and then predict the class that gets most votes, or we will take average of all the predictions, that will be the final prediction of the random forest. So now since we are always saying that if these base classifiers or base machine learning models are more diverse, in that case your performance of the ensemble machine learning method will be better. So in case of random forest, we can make it more diverse by, there are two ways. The first way is instead of searching for the best feature when we do the splitting, so at each step we do the splitting of nodes, we have already seen. So during splitting we search for the best feature and we use that feature to split that node. But what we can do here, we can search for best feature among random subset of features, means when we are splitting we will only consider few features, that is a subset of all the features. Out of this subset we will find the best feature for splitting. When we are splitting another node, we will take another subset of feature, and from that subset we will find the best feature. So in this way we will get different trees in the random forest. The second way of producing more diverse trees is that we will use different thresholds also when we are splitting with some particular feature. As we have seen, suppose we are saying if height is less than equal to some particular height, so that height generally we have seen in the method how we get the best value of the threshold here, but without generating the best value we can take different values for these thresholds, and in this way also we can generate the diverse trees. So it use random thresholds for each feature rather than searching for the best possible thresholds. So we have seen how to find the best possible threshold for different features that are used for splitting, but we can make diverse trees by not using best possible threshold. We will take random thresholds in different trees, and that is why we will get. So this is called as extremely randomized trees ensemble, or in short it is called as extra trees. So, definitely in general ensemble learning technique or in particular your random forest, it will have more bias but low variance. So, now we will see most popular ensemble learning technique, boosting. So, what is this boosting? The idea is same, we must have number of predictors and then we will aggregate output of them, and after aggregating we will get the final output. But how the training is done? Here we train all the predictors sequentially, and the objective is we are trying to correct the output of the previous predictor. So, there are two popular boosting methods. One is called as boosting, that is the short form for adaptive boosting, and another is called as gradient boosting. So, one is adaptive ADA boosting or adaptive boosting, another is gradient boosting. So, here what we are doing, we are training, or if they are having three predictors. So, your first predictor will be trained on, we can say that this is the first predictor, will provide the training data set and will get the output of this for all the instances. This is the first predictor, and then in the second predictor we will provide only those instances for which output was wrong in case of P1. Means if it is a classification problem and for these two instances or for this set of instances it was wrong classification. So, we will provide these instances to the second predictor. So, it means your second predictor is trying to correct errors that were done by the first predictor. Then again we will output of the predictor 2 we will get, but to the third predictor we will provide only those instances that were wrongly predicted by the second instances. So, so this is the main idea behind boosting. So, here predictors are trained sequentially. When this predictor will be trained and we will get output, then only we will be able to train it, because we will train it only on those instances that were wrongly predicted in the previous predictor. So, drawback of this is because this is sequential learning. So, here all these predictors cannot be parallelly trained. It is necessary that first predictor will be trained, then we will start the training of the second predictor, and so on. So, this is the disadvantage of boosting. So, what is ADA boosting? We have seen there are two methods, ADA boosting and gradient boosting. In case of ADA boosting, what we are doing, we are paying a bit more attention to the training instances that the predecessor underfitted or wrongly predicted. So, in case of ADA boosting, we can say as we have discussed here, this is basically the example of ADA boosting. So, here so in this case at the first step we give the same weightage to all the instances. So, there are chances that the first predictor, when the first predictor will be trained for selecting instances, or we can say that all instances will be selected with the same probability, because weights of all these instances are same. But when we will train the next predictor, we will increase weights of those instances for which predictions were wrong. So, we can say that when we will select instances, so probability of selecting those instances will be high that were wrongly classified by the predictor 1. Thus, in the same way we will do for the third predictor, we will increase the weights of those instances that were wrongly classified by predictor 2, and that is why we can say that these next predictors are focusing on those cases that are hard, or you can say that were for those cases for which the previous predictor made the error. So, in this way the ADA boosting is done. And finally, after training, when you are getting a new test data, so then the test data will be passed through all the models. So, these are all the predictors, you will provide the this new test data, and then output will be the class which gets the highest vote. So, your for the test, for the prediction for the test data will be same as we have seen for in general any ensemble learning technique. Now, in case of gradient boosting, that is the second method for boosting ensemble learning technique. Here what happens, as in case of ADA boosting, adaptive boosting, we have seen that we have several base classifiers, but it is not fixed that these base classifiers will be same or not. So, it can be different also. So, we can have SVM as one predictor, naive Bayes as another predictor, and so on. But in case of gradient boosting, your base classifiers are same and these are decision trees. So, if we are saying that we will have a gradient boosting ensemble learning method with 3 predictors, so all these 3 predictors will be decision tree. So, how this gradient boosting works? Here what happens, we will this is the first predictor. So, this will be trained on the instances and the output you will get. So, the second predictor will not be trained on the same instances, or it will be trained on the residual errors of the predictor one. So, suppose this is a case of regression. So, for first instance, suppose predictor value is same as the actual value. So, residual error is 0. For the second instance, that residual is suppose 4.0, for third instance it is 5.0, and so on. So, this will be trained, the second instance will be trained on these residuals. So, input and not the output, this is a residual. So, and in the same way, when you will train the third predictor, it will be trained on the residuals of this second predictor. So, this is the difference, and you will make predictions on the new instance simply by adding up the predictions of all the trees. So, this is the method of gradient boosting. So, in this lecture, we have seen ensemble learning techniques, and we have seen that in case of ensemble learning, definitely the bias error can be more for individual predictors, but variance error will be low. And then we have seen the concept of bagging and pasting. We have seen the concept of random patches and random subspaces. We have seen 3 most important ensemble learning techniques, that is random forest, ADA boosting, and then gradient boosting. So, I am stopping here. Thank you.